the cloud. All right, so thank you very much to Miles Stoudenmire, who is here to talk to us today, and to the folks who came to listen. So Miles and I actually went to undergrad together, which was a really, really nice time together, I would say, at Georgia Tech. Miles went on to get his PhD from UC Santa Barbara in 2010. After that, he was a postdoc at UC Irvine and then at the Perimeter Institute. And since then, he's landed a really nice research position at the Flatiron Institute, which I didn't know about before, but is a Simons Foundation organization that is dedicated to physics and is based in the Flatiron District in New York City. Miles is the lead developer of the iTensor software for tensor network calculations. And iTensor interface allows users to directly transcribe tensor network diagrams into efficient code, and is very useful for rapidly prototyping new algorithms, and is very much an expert on all of these sorts of things. And we asked Miles to talk today in somewhat of a response to Francesco Petruccione talking about quantum computing last week and the advantages of quantum computing versus classical computing and Miles's expertise in that area. So here, hopefully we'll have an introduction to tensor networks on this special day, and then the more full talk on Friday. Super. Miles, please take it away when you're ready.
Sure thing, I'll share my screen. How's that look?
Looks fantastic.
Okay, great. Well, thanks a lot, Will, and it's really great to be with you all here, and also looking forward to Friday. Let me get there you go, my controls working. Yeah, and so as Will mentioned, today's talk is going to be tied to quantum computing. It's not like my primary area, but it's one that over the last couple of years I was realizing has like a very, very tight connection to these tensor network methods. I mean, not just me, but people that work on these methods, but they haven't always been traditionally understood as having that connection completely. So I think we're finding more and more how deep this connection goes. And as Will mentioned, it was great to see Francesco's talk the other week. I learned a lot from that. And so this will be kind of, giving like some other perspective of what's happening kind of on the classical computing side, where ideas from that field of quantum computing are now kind of streaming back into classical computing. And we're actually getting new ideas for better ways to use classical computers, which I'll talk about on Friday, based on quantum computing algorithms that were laid down in like the 90s and the early 2000s. So let me kind of start off with that. So, so the motivation for this talk and Friday's talk is that there's a lot of excitement right now for the prospects of quantum computing, right? So you see it everywhere if you look in kind of science news, all these headlines. And here's a photo actually of a former acquaintance or colleague of mine at Santa Barbara, actually there with the CEO of Google showing off one of their quantum computers in Santa Barbara. You see these headlines about, quantum computers might destabilize the financial system because it could, crack cryptography. Quantum computing might have huge impacts on healthcare, on drug discovery, finance. You see transportation. People talk a lot about global warming. So, it sounds really big. And so, a lot of people are wanting to look into this and understand it better. And how promising is it really? But one thing you'll see in the more careful reporting on this topic is that it's really a very specialized set of methods. And it's well understood that quantum computers are not probably not ever going to be very, very general purpose the way classical computers are. And they're more like these power tools for, or potential power tools for solving sort of very specific kinds of problems. And then, to be honest, I think a lot of the experts would say, and Francesco gave a really good breakdown of this at the end of his talk, about that there's still kind of work going on to really delineate and, in what kind of limits and what types of problems will quantum computers really practically start to kind of overtake classical computation. And so there's some kind of key candidates I list here for the kind of problems where that could happen or is believed to happen. And sort of the classic ones are Shor's algorithm and Grover's algorithm. And these belong a bit more to like the world of discrete math or sort of cryptography types of problems. Shor's does factoring, and Grover's you can understand is solving a kind of inverse problem. It's saying what input to a black box function would give the number 1, all the other inputs give the number 0. Can you find that sort of secret input that kind of problem. But there's some practical questions for these. They work really well on paper, but in practice, how robust are they really going to be? And what, more importantly, maybe what's the overhead really needed? Like you might need thousands of logical qubits made out of, even more physical qubits. So there's sort of that issue. Another application that's brought up a lot these days is quantum chemistry. And again, it kind of works on paper, but in practice, will quantum computers be able to scale up to the kind of frontier of where quantum chemistry is at right now with classical computers, and how accurate can the results be made to be? And then last but not least, I think probably the most promising direction right now is physics simulation. So just quantum systems, simulating another quantum system. But then there's questions about, can we reach the circuit depths needed soon to kind of overtake classical computing? And can you reach the, for the hardest problems may have very small energy scales and demand very high accuracy. So is that going to be forthcoming? But while that's being kind of sorted out, these devices are being built anyway, and they're already doing some very impressive things, I would say. So we should be doing research to really figure out what are they going to be best used for. And one way people are doing that research, and that's what this talk on Friday will be about, is by doing simulations of quantum circuits and quantum computing algorithms. And so at the kind of simplest level, running these simulations on a classical computer helps us just to see where do things start to get hard, right? So where is that boundary between what's easy for a classical computer and what's hard? Because it's actually not as obvious of a boundary as you would think. There's some kind of naive counting you can do, but actually state-of-the-art algorithms are very sophisticated and sometimes very adaptive. And one question I'll get a lot is people will say, if I gave you such and such problem, how long would it take to do, or how well would it go? And I'm just like, I don't know, I have to try it and see. And then people are surprised by that. They'll say, you don't know? And the thing is, the algorithms are so adaptive. It's like, until you've actually tried that problem, there's like unknowns. It's kind of like if you know about factoring matrices, you don't know the rank of a matrix until you actually try to factor it sometimes. So it's kind of like that. So then in the topic of simulating, these techniques I'll talk about in depth today, called tensor networks, are more or less the most powerful current simulation technique that we have for quantum computers, for quantum algorithms. And then the most interesting thing to me these days, and this is something that's been kind of an emerging story just over the last year or two, is that at first people were interested in using the tensor networks just to do simulations, with the idea that you would do a smaller simulation to see how things would go. Then you would ultimately be thinking, we're going to run this on the quantum computer after that. But actually, the simulations are kind of working too well in a sense. So sometimes the simulations work so well that we end up just kind of completely being able to do a huge class of tasks that were originally envisioned for quantum computers. And so now there's almost kind of a flipping the script going on, where quantum, algorithms that were envisioned to be run on quantum hardware actually can be run sort of as good or even better on classical hardware through tensor network methods. And so this is kind of leading to a new breed of what you can call quantum inspired classical algorithms. So purely classical, but kind of running in the mode of quantum circuits and using these ideas. So so then let me just kind of give an outline of today and then mention Friday. So today I'll just be going through some basics, kind of laying the groundwork for what I'll talk about Friday, and also just kind of unpacking how these methods really work. So a little bit of a technical talk today, but hopefully still interesting and relevant for you all. And I'll just go through what tensors are in a kind of casual way, and then tensor networks. And then in the middle of doing that, I'll introduce quantum circuits and show how, in a sense, they are tensor networks. They're a certain kind of tensor network. And then I'll talk about how we can put all this together to actually do a simulation of a quantum circuit. And then Friday, what I'll be talking about, I might mention a kind of a grab bag of different things, but two kind of payoffs of these techniques will be one of these cases I mentioned, where there's this quantum inspired classical algorithms, where we've been able to show that the quantum Fourier transform, which is a seminal quantum algorithm, can always be done classically for a very, very wide range of inputs. Basically, like any smooth function, and even other functions beyond that, you can always carry out the quantum Fourier transform classically very efficiently. And then I'll also talk about this result that Francesco mentioned the other week, where recently there was an experiment studying the Ising model on a certain 2D lattice, and we were able to simulate that as well. So I'll talk about how we did that. Okay, so kind of heading into some background and introduction. I've mentioned the word tensor a few times, tensor networks, tensors. So in the kind of way I think about it, the way that people in my subfield are working with it, what is a tensor and where can tensors arise? And so I think the reason it's good to go back over this, like what is a tensor, is that when you look in a lot of physics texts or you learn about tensors in physics, I think they have kind of like a mystique that's put around them where you'll get to the end of like a long class on maybe math methods for physics, and then at the very end there'll be some weird stuff about like spherical tensors and tensor operators and the Wigner-Eckert theorem, and there'll be all this kind of like forbidding statements saying like, a tensor is not an array of numbers. It's actually defined by how it transforms, and you have to know general relativity. It's just, there's this kind of like fear factor, I would say, around tensors. And I would say, of course, all those statements are true, but basically all those statements are true as well of matrices. But when we talk about matrices, we don't tell students that, you can't think of them as an array of numbers. I mean, we do that all the time with matrices. So I would say that for a lot of practical purposes, a tensor is just a multidimensional array. And for the math aficionados, what I mean is that if you know the basis you're in, if you're not trying to work in a basis independent way, which in quantum computing, you do always know the basis you're in the basis of the qubits. So once you have a basis, you can always define a tensor in that basis, and then it really is a multidimensional array of numbers. So that's kind of the level I'll be using it for today's talk. And then in that sense, it's just a straightforward generalization of a vector or matrix. So, a vector is a one-dimensional array of numbers, a matrix is a two-dimensional array. Then you have a third order tensor, which you could think of as a three-dimensional array, and a fourth order, which would be, you could think of it as a collection of third orders or as a hypercube, but we'll upgrade the notation in a second to make it a little easier to talk about. And all those other sophisticated ideas about tensors are still there, but on the computer, you can just think about storing these multidimensional arrays. So, as I just said, there's a matrix, there's an order 3 tensor. We could index into it. For example, we could say, give me the 111 element, and we could get this number 3, or the 112 element and get this number in the back 5, and so on. And I think you guys know how all that works. So then where do tensors come up? So I just mentioned, things like general relativity, those are kind of familiar settings for physicists, but really tensors come up, I would argue, almost everywhere. It's as ubiquitous as linear algebra, because it really is just higher dimensional linear algebra. So one field where tensors are right now coming up a lot, and you'll see it all throughout that field, is the field of machine learning or data science. And it comes up for a very natural reason, because say if you take the example of image data, even though images are 2D, I would argue that the data kind of wants to be at least sort of a 3D tensor, a three-dimensional tensor, because you have an index that says, where are you in the X coordinate? Where are you in the Y coordinate? But then you have a kind of a third axis, which is the color and intensity of that pixel. So it sort of automatically wants to be an order 3 tensor. Another example that will be, sorry, question? Yeah.
Yeah, just a question. So would this be a tensor, or does it want to be rather a 5-dimensional tensor?
Oh, because of R, G, and B?
Yeah.
Well, I think that's a good question, but I think the problem with it being 5 is that it would be this issue of like, if you had R, G, and B separately, you may not be able to have a sense in which you have G, but then what is R doing? Like if they're separate indices, like think of them as toggling off and on or something like that, then you can't really have G being on, but then R is like off or on, I think. Like, I think it might not be as easy to, but no, I guess, yeah, we could think about that, because actually maybe each index would be like how much of R, how much of G, how much of B, right? So right. I think you're right. I think you could do that if you wanted to. So in fact, kind of building on what you're saying, there's even I'll talk about this in fact in detail on Friday. There's a trick right now that's being used pretty heavily in this kind of tensor mathematics, where in fact you want to have even more indices than that. So you could say take an R index, like for red level, and instead of just having it tick over a certain number of values, you could actually replace it by 10 other smaller indices. And then this would fill out a space of size 2 to the 10, like if each index was size 2. So you could kind of get like 2 to the 10 values for free, in a sense, just by having 10 small 2-dimensional indices. So there's actually kind of a whole movement toward having more and more and more indices. So now we're doing some calculations where we're working with things with, 30 indices all the time, because this turns out to be better than having a smaller number of big indices.
Super, thank you.
Yeah. Thanks. The other main example, and I'll get some more on Friday, but the other main example that'll be relevant for us today, where I would argue that even if you're not like looking for tensors, they just kind of pop up and arise, would be many-body quantum states. So many-body here, I mean, like, think of a collection of a bunch of spins on a lattice, or particles moving, in some number of dimensions. Or for us today, it'll be qubits. So think of these S's as indexing qubits. So they would take the value 0 or 1, just like you see in quantum computing. Then you would have your state, psi, would be a linear combination of some basis, which is just all the values that the S's can take here in this ket, making the basis. And then the amplitudes would just automatically or naturally have the same indices. And then you can see whether you're looking for a tensor or not, you get one. The amplitudes just kind of naturally want to be a tensor with as many indices as qubits. And so here I'm drawing a tensor in this so-called Penrose diagram notation that I'll define in a minute. But the idea is that many-body wave functions just are one-to-one with big tensors. So they're just there no matter what. But the problem...
Before you go on, I think...
Sure. Yeah, absolutely.
Hi, can you hear me?
Mm-hmm.
Cool. So these examples of tensors have mostly been about sort of product vector spaces, or just gluing together vector spaces to form bigger tensor spaces.
Right.
Are there examples that sort of can't be decomposed into vectors, that are just sort of innately built from tensors?
Well, so if I understand your question, then I think you're kind of in for a treat if I, am understanding what you're asking, which is that there's an extremely interesting activity that's been kind of happening over the last 5-10 years, which is connecting tensors to the idea of like category theory. But sorry, are you familiar with that topic actually?
Oh, yes. Oh, I know about category theory. I don't know about its tensor connection just properly.
Sure. So, I mean, the way now that's it's a big topic and it's often presented extremely abstractly, but there's a much more practical kind of tensor end of that field, as I understand, that I've been kind of looking into myself recently. And one way to understand that field, at least my understanding of that field, is that you can think about spaces which are not like bases, which are not easily constructed just by taking kind of free, tensor products. But you have to involve linear combinations of the basis vectors to define the basis.
Right.
And so this actually kind of very naturally is expressed in the language I'm going to develop today. So you don't see this in many papers, but these kind of fusion trees, these kind of fusion diagrams that define those things, these like modular tensor categories, unitary fusion categories, they actually are in many cases identical to matrix product state tensor networks. But it's not something you see written very often. But at least for the example of groups, like abelian and non-abelian groups, these tensor networks are the kind of natural language in which to express those constructions, and the tensors are the Clebsch-Gordon coefficients. So you can definitely use all these together.
Right. Okay.
Sure. Absolutely. Yeah. So the problem with this, though, so here I'm saying, if you want to do quantum mechanics of many particles or qubits, use a tensor, but that actually goes very poorly if you do it naively, and for all the same reasons that many-body quantum mechanics is hard for other methods. And it's for a very simple reason, and mathematicians and applied mathematicians call this the curse of dimensionality. In physics, we call it, say, a many-body problem. And it's just that if you do simple counting, you say, what if I had some number of indices? Here I'm being concrete and saying we have 6 indices, and let's say each index ran over 10 values each. Then very simple counting will tell you that there's 10 values of the first index, 10 of the second, so on, so on. So you get 10 to the 6 numbers inside of this tensor. So if you actually tried to store it in a computer, you could do that. But once you had 7, 8, 9 indices, you'd just blow up all your memory very fast, and your computing time would grow exponentially as well too. So in general, if you have n indices, you're going to have something like d to the n entries, and the number of entries grows exponentially, and that's a very, very hard exponential, and sort of, you can make a whole supercomputer freeze in just a minute if you try to input a tensor like this. So another problem with tensors is that they're hard to use in kind of traditional notation. So they're hard to visualize beyond, say, second order tensors, third order tensors. The notation gets kind of unwieldy, all these indices, and you have to think of names for all the indices and everything. So fortunately, there's a way out of these problems. So which is this these kind of notational problems, and in a minute we'll see a way out of this cursed dimensionality problem as we go through the talk. These notational problems I mentioned, there's a really nice way around these, which is the so-called Penrose tensor diagram notation. And I want to emphasize that these look like drawings or schematics, but they're actually a rigorous mathematical language. So it's a totally rigorous notation. And the notation works like this. So there's basically two main rules, and the rest are just conventions that different authors sort of adopt locally to their work. But the two sort of hard and fast rules are that a tensor is notated by a shape with some number of lines coming out, and the lines correspond one-to-one to the indices. And you can label the lines with the index names if it's helpful. But one good thing about the notation is as you use it, you can sort of start dropping the names, and the lines just take over, and you don't have to actually think of names, especially for dummy indices that don't really need names. And these are some examples at the bottom of low order tensors. So like a vector is just a shape with one line, and a matrix is a shape with two lines, and a third order tensor has 3 lines. And the orientation can matter in some more exotic settings, like in the category theory settings, but most of the time the direction of the indices is pretty much up to you and just whatever is convenient. The other main rule of this notation is that, kind of in analogy with Einstein summation, if you join 2 of the lines, then automatically there's a summation implied over the joined lines. So the idea of it is that here on the right would be a traditional expression for multiplying a matrix M times a vector V. And then very often you have to kind of go hunting through the indices to see where are the ones that are summed over. And then some people will draw a line just as a guide to the eye to say, here's J and here's the other copy of J. And then the idea in this Penrose notation is that you get rid of the letters, you get rid of the sum symbol, and that line becomes the whole thing. And so just that line tells you there's a sum running, and that's the same line connecting these indices here. And another benefit is that you can just by inspection see what kind of object results from the contraction. So you can see that even if you didn't know anything about matrices and vectors, you just look at this drawing and you see that there's one line sticking out. So you know the result is a vector just from inspection. So similarly, you can look at this diagram and see that the result has to be a scalar because there's no lines left over at the end. And it's when you kind of unpack the details, you can see that it's the trace of a product of 2 matrices. And one nice thing about it is that you can prove theorems sometimes with this notation, which is that if you just look at it like kind of topologically, this blue bead can slide all the way around the back of the wire, and you'll get the same diagram. It'd be the same number. And so that's like a proof of the cyclic permutation property of the trace, just kind of visually. So it's like a nice language that way too. And then, last but not least, but this is maybe the most important part about this notation, is that when you're doing tensor networks, you encounter expressions like this. This is actually the most elementary type of tensor network that I'm showing here in traditional notation on the top. And I'll go through later how it is constructed. But it's pretty awful to write, and you have to think of names of indices, and they have subscripts, and you have to kind of look very hard at all the indices. And it's kind of hard to tell just from the above what's actually going on. But in the diagram notation, it's a lot clearer. You have a big tensor with 6 indices here. And then I think I have the wrong number up top, but never mind. And then what it's saying, what this expression is saying, is that we want to factorize it into a chain of tensors that are all connected on one shared index between these pairs. And each one in the bulk has 3 indices. So it's a lot clearer. And then even these indices, these dummy indices called A up here, in the diagram notation, you can just drop them. And if you want, you can even drop the outer indices as well, without really losing any essential information. So that's a really helpful notation. Of course, it doesn't depict everything, but it kind of depicts the most important things for the kind of calculations I'll be talking about. So I put like kind of a pop quiz just to see if everybody is like tracking with the notation. So if anyone wants to speak up, how would you describe in words the first diagram at the top there?
Is that just the inner product between 2 vectors?
Yeah, thanks, Daniel. That's a vector inner product. Great. How about the second one, someone?
Trace.
Great. Okay, just a trace of a matrix. And then last one doesn't have a special name, but just kind of in words, what would be a good description of it?
Would that be multiplying a 3rd rank tensor into a vector? I guess contracting A third rank tensor. Yeah, okay.
That's right. Yeah. So there's no real special name for it, but exactly, it's just a kind of some kind of product of a vector with a order 3 or a third order tensor. Exactly. So and then you can see again how, as I kind of wrote the traditional notation, you know, I put letters and names for all these things, but you actually don't have to. You can just draw it like this. But then just if you want to connect to traditional notation, there you go. Okay, thanks everybody. So now kind of one of the main points I wanted to make, and it may already be obvious to some of you, but I think it's kind of like a non-trivial connection, is that whenever you see quantum circuits, you're always looking at a tensor network. That's kind of the point of this next part of the talk. So let me kind of go back through at a really simple level, like what is a quantum computer? What's kind of quantum computing at its essence? So a quantum computer, as we all know, is a machine made of quantum bits, right? So unlike classical bits, quantum bits, you know, they act a little bit like a quantum spin or something, where they could be in a kind of a classical state up or down, but they could also be in some kind of quantum state, like, you know, plus X, minus X, this kind of thing. And then most importantly, they can be in superpositions and they can be entangled with each other. And because of this entanglement that you can make them be in, you can have them explore an exponentially large state space. So you can input very precise instructions, and after you do enough of these instructions, which are these gates, you're moving the state vector further and further out into the depths of kind of the deep part of Hilbert space, and you can use this very large state space in principle. And then the program for a quantum computer is called a quantum circuit, right? And here I'm just showing some kind of example of a made-up quantum circuit, actually kind of motivated by Google's random quantum circuit experiments, but that's not going to be so important for what I'm going to say here. So here on this slide, the point of this slide and the next slide is to say, this is what you would see as just kind of a typical example of a quantum circuit in a quantum computing textbook. And the idea in those books would be that these are just schematics. It's just saying, these are the qubits over here. And then there's gates. And then these gates are not really, you know, the main point of them is that you would draw them out, and then you would go tell an experimentalist that this gate means to go fire some kind of certain microwave pulse at this qubit, and that will rotate that qubit. And this gate says, you know, do a different pulse on that qubit, and so on. And this one might say, do some pulse that acts on both qubits. So it's like a set of instructions for this quantum computer. But there's another point of view, which is that this is the same drawing as a tensor network, right? So I didn't change the diagram at all, but I would argue that this is also a drawing of a tensor network in that same Penrose diagram notation that I mentioned earlier. And that's a powerful thing, because then it's saying something, which is that we could, in principle, compute the output state of this circuit just by contracting tensors in a classical computer, right? So all of these boxes now can be thought of as just some kind of tensor of, you know, order 2 or order 4 that we could store in a classical computer. And then just by doing, you know, additions and subtractions and multiplications, we could carry that out. And then most importantly, it doesn't matter what order we carry it out. So instead of just working from left to right, we could work from top to bottom, or from the middle to the side, or any direction we want, whatever is the most convenient for the classical computer to do the least amount of work to compute this output state that's a tensor defined on these open legs over here. So let's kind of see in detail how this works. So first of all, we could think of the initial state as a kind of tensor network, because we could initialize the qubits into just a product state that's all the 0 state. This is a very typical convention in quantum computing, just to start from the product all 0 state. So let's just take all the qubits to be in that state. And mathematically, what this means is that we've taken an outer product of a bunch of vectors. So in the kind of computational basis, these are the vectors 1, 0, and we've taken an outer product of them. And already that's formally a 2 to the n dimensional vector, but it would be pretty foolish to actually store that vector, because we know it's just the outer product of these 2-dimensional vectors. So we actually just want to store those, just the 2-dimensional vectors, kind of implicitly next to each other, and not actually take the tensor or outer product, right? And that's kind of the whole trick with tensor networks, is that everything is formally in some kind of exponentially high dimensional space, but you're trying to store these pieces and kind of hold them apart. And these pieces are going to be small, just like how these vectors are only 2-dimensional. And then next we have the single qubit gates, and that's, you know, depicted as this first row of gates here. And these are just some matrices, right? They have 2 indices. For example, we could have a single qubit gate that's a Hadamard gate, and that would just be this matrix, or a NOT gate, a different matrix. And then last but not least, we would have 2 qubit gates. And these 2-qubit gates, and of course you could have higher qubit gates. These we could think of as tensors with 4 indices, right? 2 incoming, 2 outgoing indices. And that makes them, if you want to think of them as a matrix, just in terms of merging these ingoing indices together and the outgoing, we could think of them as 4x4 matrices in some sense. And this would be, for example, the matrix of the controlled knot gate. And there's many other kinds of 2-qubit gates you can write down. So as I mentioned, if you could contract all these tensors, you would just have the state that would be of the quantum computer after you executed that circuit. So we can kind of do this a little bit ourselves by hand without using any kind of, like fancy computing, just to kind of see how this goes and why it gets hard, right? So as I mentioned, we can actually write the entire quantum state, this entire many-body quantum state very easily at the beginning, where there's like an implicit outer product or tensor product between these vectors. So that's how you would write down this initial state. So that's the initial state. And then we can act with Hadamard gates, for example, on all the qubits. And then already we can see kind of an important point. So that turns each of these vectors into the vector 1 over root 2, 1 over root 2, and I've just collected the norm here on the side. So we could see something kind of important, which is that already this is a many-body quantum state, but we can still just like look at it mathematically and store it very easily on a classical computer, despite the fact that it's in a massive superposition. This is actually an equal weight superposition of all the vectors in the Hilbert space, like all the basis vectors, right? But it's very easy to write down and store the whole thing. And the reason is basically because it's unentangled, right? It's still a product state. So it's just a tensor product of a bunch of vectors. But then when you start acting with 2-qubit gates, you start introducing entanglement, and then things get more demanding to write down or to store in a classical computing scheme. So we could act with, for example, a controlled Z gate on qubits 1 and 2. And then now afterward, we can no longer write their states of qubit 1 and 2 as a product of 2 vectors. It really is just some kind of matrix, a matrix because it has 2 indices sticking out here, right? And it's, in particular, it's this matrix. And if this was some other gate, it might be some arbitrary complicated matrix. Then we can do the same on, I was going to mention that has now introduced entanglement between qubits 1 and 2. I'm not going to formally define entanglement, but you could just think of it here as the fact that there's correlations here between these in some kind of irreducible way, and we can't simply factorize them back into vectors. We could do the same on qubits 3 and 4. So now we have entanglement between them. We have to write their state as a matrix, not 2 vectors. And then on 5 and 6. So now here's the quantum state after that, those 2 layers of gates. So we can do all of that by hand up to that point, and maybe you can go a little past that point, maybe acting on qubits 2 and 3, and then this thing would combine into some kind of 16, some kind of 16-dimensional object, that kind of thing. But after that, it just gets too hard to do by hand. So once you do a few more layers of gates, very quickly, the state of the system is really just now some complicated tensor. And I say a tensor because, as we mentioned earlier, it's a quantum state of, in this example, 6 qubits. And you can think of it as just, I contract all these tensors over here, and in the end, I just get some big blob that has these 6 lines sticking out. And there's some complicated numbers in here. And basically, these numbers have very little discernible structure. And in a sense, their only structure, if this was sort of a very deep circuit, is just the structure of the circuit itself, if these gates, say, were random or complicated in some way. But there may be other cases where the circuit carries out some very specific program, and maybe that program has a lot of extra structure, and maybe the answer simplifies, and maybe we could like take advantage of those simplifications and be smart about how we stored the tensor. And we'll see now some techniques to do that. But the point being is that quantum computing, again, kind of forces you to encounter large tensors. The state you get after a circuit of sufficient depth is just a big tensor. So then it just begs the question of, what if there was a way to work with large tensors in a classical computer? What would be the implications for quantum computing? Is there such a way, and what would be the implications of that? And it turns out there is a really nice way that's a very natural fit for quantum computing, and that's the idea of a matrix product state, a tensor network. Let me just check how I'm doing on time. So, okay, great. If you kind of go back through the field of classical computing and people trying to deal with tensors and dealing with very high dimensional spaces, there's a few ideas actually of how do you get around this problem of the curse of dimensionality, the problem that you cannot store or work with a tensor that has n indices where n is, say, bigger than 40 or so, if they're all of size 2. It just gets exponentially costly and very, very prohibitive. So there's actually a few different ways out of this problem, and some are more limited and some are much more wide-ranging and much more general purpose. So briefly, the more limited ways are ideas like sparsity. Like one idea that comes up a lot is the idea that maybe many of the entries of this tensor are 0 or nearly 0, like we can kind of threshold them down to 0. And that can be the case in sort of special domains. Like for example, if you have data and you have samples, you usually have way fewer samples than the space of all possible samples. So if you thought of this tensor as being holding your data, most of the entries will be 0. So that's a very powerful idea in that setting, but it's kind of limited in the quantum setting because we could see, in this example, even after a couple layers of gates, all the elements are non-zero. So, or even at the first layer, they're non-zero. So sparsity isn't going to help us so much here. And then another idea is sampling. So sampling is saying, okay, maybe all the elements are sizable. It's just that some elements are the biggest. We have some elements that are much, much bigger than the other ones. And we just spend most of our effort going after the biggest ones and the second biggest and the third biggest ones and kind of sampling down the tail, and we'll get the biggest weight part of the tensor that way. And that can work very well. It's just that in the quantum setting, you have negative numbers as well and complex numbers. And that can really be a problem for sampling. And that's known as the sign problem. So that can be a big limitation of the idea of sampling in quantum systems. So finally, the idea we'll use today is the idea of low rank structure, and I'll unpack that in some detail. And that turns out to really be kind of more powerful in some sense than these other two, I would argue. It's kind of like sparsity, but it's the idea that it's the idea of combining sparsity in a sense with a change of basis. It's saying that in the original basis, everything is non-zero maybe. But if you could find some special basis, a bunch of things could become small or 0, and then you could threshold them away. So that's one way to understand low rank structure. And so the nice thing about low rank structure is that for matrices, it's basically a solved problem. I say basically because there's still some pretty interesting developments going on in this field, even for matrices. But in a sense, this is like a solved problem, very nicely solved by a technique known as the singular value decomposition that I'll kind of go through in a second. And all I mean by low rank structure is that if you're given some matrix M, let's say some kind of square matrix M, but it has some kind of hidden structure in it. So the numbers follow some kind of smooth pattern or are somehow related to each other in some way, even if that way is hidden on first view, you can discover that the matrix might be low rank. And all that means is that it's a product of two smaller matrices, like a tall, skinny matrix and a kind of a short, wide matrix, A and B. And technically, it just means that these other two factor matrices, A and B, are connected by a shared index summed over that runs over R values, where R is called the rank of the matrix. And this can be an approximate statement, right? It may be that technically R is as big as it can be, but you can kind of choose it to be smaller and make some kind of approximation error that's small or controlled. And the SVD tells you how to discover these matrices A and B for any matrix M in kind of like an optimal way. And what it does is it outputs 3 matrices. You kind of want 2, it outputs 3. And it outputs a unitary matrices U and V and a diagonal matrix S. And you can always, if you want, just take the square root of S and push it into U and V and get this A and B if you want. Let's see an example of the SVD. I mean, I think many of you may just know this by heart, like how the SVD works, but I just thought I'd go through it. Let's say you have some kind of example of like a rectangular matrix. And the nice thing about SVD is it works in rectangular matrices, singular matrices. We can run the SVD algorithm and it'll output these matrices U, S, and V. And a nice thing about it is that S is always guaranteed to be diagonal, and its diagonal entries are real and non-negative and decreasing. So it's a very nice kind of output. And the most important thing to understand about it from my point of view and what we'll be doing here is that you can develop a controlled approximation for the original matrix by just truncating away the smallest elements of S. So you can say, here's the last element of S is small, it's 0.2. So I can just throw it away and set it to 0 instead of 0.2. And the neat thing about it is that as you're throwing away these singular values, if you keep a table of which ones you've thrown away, the error you're making back to the original matrix is nothing but the sum of squares of the singular values. It's given by that. So you can actually see that that's exactly the error you're making. And then we could throw away the next singular value and we'll make a bigger error, but we'll know exactly how much error we're making. And once we've thrown away a certain number of these small singular values, we have all these zeros here. So we can throw away the corresponding rows and columns of U and V. And then what we do is we get a compression. So instead of having to store 12 numbers up here, we can store much fewer numbers here. We just store the important columns of U and of V and singular values S. And again, we know exactly how much error we made in that truncation process. So, and then you can prove that actually the SVD is the optimal low rank approximation. It gives the optimal one in a certain sense of a kind of norm distance back to the original matrix. Okay, so that's kind of the most technical part there. So that's defined for matrices, right? So then a question would be, how can you generalize the SVD to tensors? And this is actually a whole field of people asking this question, and there's many different answers. But one of the answers you can give to this question is to say, well, every tensor actually gives you a set of matrices, and it's a very simple idea. You just reshape the tensor as a matrix, and you'll see there's more than one way to do that. So you can say, given some tensor with 4 indices, I'll just treat the first index as a row, and the other 3 collectively as a mega column. Like I'll just kind of fuse them together temporarily into a big column. So let's say these all had size 2 indices. This would be a column of dimension 8 now, just temporarily for this purpose. And then you can call the SVD on that and get some factors USV. But then the interesting thing is you can do that another way. You could partition the first 2 indices to be the row and then the last 2 to be a column and call an SVD on that. And these would be a different US and V. And then you could also cut there as well and get a third US and V. And these would all be in principle different matrices coming out. But then they have to be related in some way because they all came from the original tensor. So this kind of begging the question of, okay, how are they related? So are they related? And the answer is yes. And the detailed answer to this leads to the idea of a matrix product state factorization of a tensor. So I hope you can bear with me for this kind of more technical part of the talk, because I think it's interesting. I wanted to kind of leave this in the slides. So what we can do is we can just kind of chain an SVD left to right. And when we're done, what we'll have done is we will have factored a big tensor into a tensor network in some kind of principled and controlled way, just by doing a sequence of SVDs. So, so any questions at that point about any of that?
So I guess on the far left, you've got, or I guess now we have the dotted line on the far right. The far right thing is a matrix.
Mm-hmm.
And then the next thing is a 3 tensor and a 3 tensor and then a matrix.
Well, the way I'm seeing it is that this is still, the top 2 are still just 4 tensors. They're still tensors of 4 indices. But it's just that in the middle line, I'm now viewing it as a very rectangular matrix. So it's still the original tensor. All the numbers are the same, but I'm just kind of, it's like if you call reshape in Python, if you know that command, it's just saying like, take the first 3 tensor dimensions and just kind of clump them all together as some enormous row dimension. And then the last index, take it to be a column, like a small column dimension.
Well, I guess that makes sense, right? That you're taking those 3 indices on the left and you're treating it as a direct product to produce huge matrix.
Mm-hmm. That's right. Yeah, you can think of these 3 indices as collectively ticking over 8 different values. Like if they're all size 2 indices, then I could have 111, 112, 121, 122, all those 8 different values. They could form a 8-dimensional row space. And then the other guy would just have 2 values, so it'd be a 2-dimensional column space. So then this would just be an 8x2 matrix, but all the numbers are just the same numbers as the tensor on the top, just kind of reshaped into that 8x2.
It looked like Daniel had a question.
Mm-hmm.
Yeah, it's a sort of scratching. I'm not sure if it's correct. So if you were to just like keep reshaping and keep reshaping, do not sort of break the SVD decomposition. Does your S matrix, do you not just end up with a row vector times a column vector, as 1 by 16 times a 16 by 1, and then your S sort of does nothing?
Mm-hmm. Yeah, you do. So you could actually move this line if you want. You could move this line past the end, and then you could just have all 4 indices be the row, and then the column you could put a fake dummy index of dimension 1 if you want, and then S would just basically capture like the norm of the whole maybe like the square root
yes.
norm of the whole tensor. And then U would just be the tensor thought of as one big normalized vector or something like that.
Yeah, okay.
It's a good question. Yeah. But it kind of shows the power of the SVD that it somehow always succeeds even in these very extreme scenarios like that, which is it's like an interesting point, I think. Yeah.
Yeah. Okay, thank
Great.
you.
Okay. Thanks. So that's the idea, is that every tensor kind of could temporarily be a matrix, and then you could kind of fold it into a matrix and unfold it back. But then there's more than one way to do it. And so this is kind of a hint that there might be some kind of shared compatible multi-SVD of a whole tensor, and that's the idea of a matrix product state. So here's kind of the whole algorithm. And so sorry, this part's a little technical, but I hope now that with that background, you can follow it. You all can follow it. So so the idea goes, sure. Do you have a question?
Yeah, just on I'm also more on the side of tensor is a thing that transforms like a tensor. I'm from that that sort of background.
Sure.
So when you do this sort of merging of indices, do you have to sort of keep track of where you've merged in a sense? Otherwise, you're going to lose your transformation behavior. Or is that not really important?
It's actually very important. Yeah, it's a really good point. So in the more casual settings, like if you're actually quantum computing is kind of one of the more casual settings in a sense, where the most important thing is just to keep track of how the qubits were ordered. So you would just say, it's a great question. I mean, it's like you just say, when I merge them, I'll take this guy number 2 to say be the fastest moving index, and then 3 will be the next fastest, and 4 will be the slowest. Or sorry, the other way around. Maybe you'd say the slower and then faster and faster. So you might go 1, 1, 1, 1, 1, 2. Here I'm doing 1 indexing, and then you'd go, 1, 2, 2. Sorry, 1, 2, 1, 1, 2, 2. So this guy's always moving the fastest. This is the second. You'd have some notion of that, and you would have to bookkeep that in the computer when you make the matrix. And then all that really does in the end is you get your V, and then you just have to be consistent and say, when we unpack V back into a tensor, that's what you do at the end, is you treat V as a tensor. You just have to consistently unpack it back. But this can be much more non-trivial. Say if you wanted to, with this, something that actually some tensor libraries offer is you can actually conserve non-abelian symmetries like SU2 transformation properties. And there, it's much more complicated, because when you merge these indices together, you actually have to develop you actually have to kind of tensor product them, decompose this into irreps, and then you actually do the SVD through the irreps, and then you have to undo all that back. So it's like a lot more complicated in that case.
Okay, yeah. Thank you.
Sure. So I was hoping that was kind of a satisfying answer at the end, because all the more higher level mathematics of having to decompose tensor products into sums of irreps, that becomes essential actually when you're trying to preserve those symmetries through the SVD. Great, thanks. So then with that kind of armed with that tool, like that kind of ability to SVD a tensor instead of a matrix, here's kind of an algorithm that you can work out. And the idea is now we just do those SVDs that I drew, but we kind of pass the output of one into the input of the next. So what you do is you say, start from the left, and let's have the row be the first index, and then the column will be all the other indices. And we'll do that kind of consistent packing and unpacking that we just talked about. And we'll do this SVD. And then the V will have a bunch of indices, and we could unpack them back into a tensor if we want, or just kind of leave them grouped. And then what we do is, the first thing you do is you say, let's multiply S over to the right, because we're going to be doing kind of a left to the right pass here. And that will just make some other tensor. I'm not giving it a name, just calling it S1V1. And then we can think of U as being kind of done, like it's an output of this algorithm. So we can just say thank you to U1, and it's done. And it goes off, and we just detach it over to the left and hold on to it for later. Then we take this tensor, this kind of remainder, this S1V1, and we can look at it carefully and see it's a tensor of 4 indices, just like the original one. Although now this one is some kind of new index that was introduced by the SVD. And now we can cut, for the rest of the steps, we'll cut after the second index. So we'll cut there. And we'll have the first 2 indices divided off as the row, and the however many are left over on the right will be some kind of collective column. And then we'll do the same process there. I'm just drawing U1. U1 isn't really doing anything now, it's just kind of along for the ride. But then U2 is now produced by this next SVD, as well as an S and a V, and we'll multiply those together and get another remainder. we'll kind of say thank you to U2 and it's done. So we have U1 and U2, some remainder made out of these. And again, we'll cut here, and then we'll get a last SVD, U3, S3, B3. And then now we have 3 different U's, and notice each one is carrying an original index of the original tensor. And then there's this guy at the end. And we can kind of clean up at the end by multiplying the S3 over into the last tensor, thinking of that as some remainder. And then we can rename all these guys some generic name and say A1, A2, A3, A4. And if you want, you can remember how they were made, and that can lead to some important details about some kind of, we call this like a gauge actually in tensor networks. You can think of it as kind of a gauge condition, so an internal property that you can put on these tensors, but that's a bit advanced. But basically what we came up with is a factorization of this tensor into 4 tensors, as many as there were original indices. And what's neat about this is you can do that truncation that I talked about as you go. So if you encounter small singular values and you're working up to some certain accuracy goal, you can throw away any singular values whose squared sums fall below that accuracy goal, and you can get a compression. So you may find that these indices, these red indices going through, do not end up having to be as large as they could be. You might be able to take them to be a lot smaller and get a major compression of this original tensor that way. And so from that point of view of that algorithm, this is what an MPS or matrix product state is. It's a multi-SVD of a tensor. So it's like a chained SVD of a tensor. But there's another point of view that'll be actually more practical, which is to say, we can't really practically always do that algorithm, because what if the original tensor was so big, we couldn't even form it in the first place? How would we have done the SVD if we can't even store it in our computer in the first place, or if we don't even have it in our hands? So really what you do is you imagine that whole process having been done, and then you just think of this space of tensor networks on the right as a kind of special manifold or subspace of tensors. You think of it as a low rank subspace where you say, this is a special class of tensors that are decomposable in this way, and we will just work in that space. But what's neat is that there's algorithms that let you kind of always work in that space. I'll say more about that in a second, and even let you move between these spaces. So you can kind of move from a very low rank space up to a slightly higher rank space and back, and kind of move all around in these manifolds in really nice ways. So it's really like a whole toolbox you can think of as a way to kind of carve off a really big piece of tensor space and work efficiently on a classical computer. So one question might be, why is this thing called a matrix product state? I mean, you can kind of roughly think of the name as coming from how we took products of matrices that came out of the SVD. But the real reason for the name is that, and this is to show you an example of the kind of algorithms you can do, is that you can retrieve components of the original tensor by multiplying matrices. That's where it comes from. So the original tensor, if you'd stored the whole thing, you would retrieve component by just going into memory of your computer and grabbing the component and pulling it out, right? So there wouldn't be any algorithm to really do. But here, what you've done is you've traded off memory for computation, and you said, to get an element out, to get a component out, we actually have to do a small computation. But that's kind of how we're able to save all this memory. It's by kind of trading memory for computation. So let's say we want the 0, 1, 0, 1, 1 component of the original tensor, which we're storing kind of implicitly as this matrix product state network. Then what you do is you set the indices to those values. And when you set them to those values, you can think of them as frozen. And so we can erase the indices, and we can just now think of having taken slices of these red tensors. And when we look at these slices, the first one is a vector. It has one index left over. The other ones in the middle are all matrices. They have 2 indices left over because we froze the outer one. And then the last one's a vector. So really, this is just a chain of vector, matrix, 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 vector product. That's where the name matrix product state comes from. And then we just do this product, and we can do it very efficiently. We can multiply the first vector into this second matrix, get a new vector here in blue. Repeat, we can say vector times matrix, vector times matrix, vector times vector, and we get a number, and that number is our approximation for that tensor component. So any questions about that slide? Because that's kind of a whole algorithm there that I just showed. Okay, great. So then I'll just kind of end this part of the talk with kind of some key points, some key takeaways about this technology. So that was the most technical part there. The key things to know about this kind of tensor network, it's not the only kind of tensor network, but this is maybe the workhorse or sort of the core original tensor network, the matrix product state. is that it has a key concept called the bond dimension or the rank. I mean, I think rank could really be a better name for it, but a lot of physicists will say bond dimension. And that's the size of these internal indices that go through the network and that connect these kind of latent tensor cores or tensor factors that are these red tensors here on the right. And I'm showing it here as a single number. I'm saying chi. Actually, it could kind of vary as you go across and kind of adapt for the problem at hand. But just for simplicity, let's think of it as, say, the maximum over all of those. The idea is that if you can get away with a modest value for this thing, if it could be 10 or 100 or maybe 1,000, then if that gives you a good approximation back to the original tensor that you're trying to model, then you obtain a massive compression. So you've really broken the curse of dimensionality and by an exponential amount. So before you would have, if all these outer indices were dimension D, you'd have to store D to the n numbers inside of this huge blob, and that's really impossible for large n. But over here, if you just do some counting, each of these tensor factors just has D times chi numbers inside. So D chi squared numbers, and there's n of them. So you can just see by counting that the n comes all the way down in front, as long as the chi can be thought of as a constant. And so in practice, this often happens. So many ground states, for example, of many quantum systems, this chi, you can get away with a chi of like 100 or something and get extremely good results. But then on the other hand, what's nice about this too is that you're not really losing anything in principle in terms of representation power, because you can always take chi big enough to represent any tensor whatsoever. It's just that you may have to take it to be exponentially big. So you hope you don't have to do that, but you could if you need to. So you haven't really restricted yourself in that sense. One other important thing to understand about this factorization is that it's directly tied to the notion of entanglement. So I'm not like formally defining entanglement here, but you can define entanglement actually through the SVD. And think of it as just kind of like a weighted rank, weighted through those singular values, which in quantum mechanics are called Schmidt values, but it's the same thing as singular values. And more simply, what happens with an MPS is that if you have an MPS representation of a quantum state or kind of amplitude tensor, then it's easy to show that if you ask about the entanglement for between region A and region B, you say how much entanglement is there, you can provably upper bound this. It's actually not a hard proof at all by the value log chi. So if this bond connecting the regions is size chi, then the most entanglement there can be between A and B is log chi, and in practice it's less than that. And so what this tells you, kind of flipping that statement around, is that matrix product states are good at capturing low entangled states and moderately entangled states. So basically, if you think of the entanglement as kind of growing and growing and growing inside of a quantum computer, it's going to push this chi up. The chi has to grow. And at some point, that chi will get too big, like once it's, say, bigger than 10,000, then the classical computer can't keep up anymore. And it'll blow up the classical computer and you can't really do it anymore. But as long as the entanglement is moderate, chi can be reasonable, a few hundreds or thousands, and then we can do this very easily on a classical computer. We can keep track of all these numbers, no problem. Okay, and last but not least, maybe one of the most interesting things about these tensor networks is that you can develop a bunch of really interesting and powerful algorithms, all in terms of these networks. You don't actually have to leave this compressed form. You can stay entirely in the compressed form and do things like summing to MPS or multiplying an MPS by some kind of linear operator. That's another type of tensor network. Again, always staying in the compressed form and returning another compressed matrix product state. There's even a perfect sampling algorithm where you can actually draw samples, just like how on a quantum computer you could sample the state at the end and get a bit string. You can also draw bit strings from these tensor networks. And it's a Markov chain free Monte Carlo algorithm where you get sort of perfect independent samples of the distribution represented by the tensor network. And then just to give one more example of a concrete algorithm you can do with them is you could say, I have two quantum states represented by these tensor networks and I want to know their overlap. I want to know the inner product between them. But the idea would be if each of these is representing a tensor that had 40 indices of dimension 2, then that would be a dot product of two vectors that are a trillion with a trillion entries. So this could be really prohibitive. But or especially if there was more than 40 indices, 50, 60, it gets really bad really fast. But when you represent these as these tensor networks, there's actually a really nice trick, which is you can draw their overlap as just this network, and then you can contract it from the side. instead of thinking of these as two huge vectors, you can just say, I can contract this any way I want. So you could merge these first two tensors into some matrix I'm drawing in gray. And then you can keep merging the next tensor over into this matrix and sort of sliding it through from the side. And when you do that, that algorithm only takes like 10 milliseconds on a laptop, as long as the chi is a few hundred. And for basically any length, any size system you want, you could do 1,000 qubits if you wanted, no problem. It would just take 100 milliseconds or something. So it's very, very efficient. And then just, I won't go into it at all, but this matrix product state is not the only kind of tensor network. It's just sort of the oldest and the most well-developed one, but there's others that are in the form of trees, or you can make tensor networks that match a 2D system or a 3D system. And these are the kind over here that people are investigating for things like lattice gauge theories. And I'll also mention them on Friday for this simulation that we did. They're called PEPS tensor networks, and they kind of match the lattice that you're on. Okay, I think I have maybe like 10 more minutes. Is that right?
Yeah, keep going.
Okay, great. I think that's all I'll need for this last part. So hopefully most of that made sense about the kind of technical side of tensor networks. So let's kind of now lastly put it all together and see, like, with that toolbox of this matrix product state, how could we actually simulate this quantum circuit now, like in an efficient way rather than a very inefficient way? So the inefficient way would be to just kind of give up and say a quantum state is this tensor with as many indices as qubits, but then we would be doing something exponentially scaling and we would have a pretty bad time. But this tensor network gives us a way out of that problem. So the way out is to say that we might have some hypothesis or just kind of be bold and just kind of hope that maybe if the circuit solves some kind of real world problem, like some structured problem. So there are these ideas in quantum computing, for example, like called QAOA, where you're solving some kind of graph theory problem, like a min cut of a graph or something like that. And graphs have structure, right? Like every graph has some kind of actual details. Maybe those details, because they're specific and concrete, maybe the state isn't going to be the most arbitrary random state in the whole Hilbert space. Maybe it'll be some particular state that has some particular structure, and we could compress it into an MPS. But how can we actually use that? So what we can do is we can think of the initial state of the qubits, if say a product state, trivially as a tensor network already, by just imagining there's these bonds connecting down. They're not there, but we could just imagine they're all there in just dimension one. So we can already think of them as being a matrix product state tensor network. Then we can act the single qubit gates on those, no problem. It's still a matrix product state. Then we can act the 2 qubit gates, and I'll show you in a second how to do that. And now we get some entanglement. So now we have these bonds running through, but they're small because we don't have very much entanglement, but there's now some. You can act the next single qubit gates, 2 qubit gates. And now I've drawn this line getting thicker. So the rank of this matrix product state, which I'm drawing sideways in this picture, is getting bigger, but it doesn't immediately grow to as big as it can be. It just grows slowly as the entanglement starts to build. We do single qubit gates, 2 qubit gates, it's getting more entangled, more entangled. And then what's neat is if this goes well, if you run that kind of simulation where you keep your state as this MPS the whole time, you're actually doing something much more than what a quantum computer can do. A quantum computer can do that circuit, but at the end, all it can give you is one sample. You look at the state and you get a bit string out. Of course, you can get it out at any basis you want, which is nice, but it's still just going to be zeros and ones coming out. Here, if you can pull this off, if it works, you get the entire quantum state sitting on your computer as this MPS, and then you can do all kinds of things with it. Not only take samples, but you could compute correlation functions, you could study it in all kinds of ways, look at its entanglement properties, all these things in efficient ways. So let's see how to actually do that process that I just kind of showed an animation of. Like, how could we push an MPS on the side here and the quantum circuit through a quantum circuit? How do you actually do that? So the idea is that you would just say, kind of working recursively, like let's say from the previous layer, we already had an MPS coming up to this point. And now we want to act the next set of 1 qubit gates and 2 qubit gates onto it. And as I mentioned, it's kind of trivial to initialize because we just initialize to a product state easily. So how do we do that? Given an MPS of the previous layers, how do we go and apply the next layers? And all we need to do here is be able to apply 1 qubit gates and 2 qubit gates in this setting. And what's nice is we'll see 1 qubit gates you can always do completely numerically exactly on the computer for very low cost. And 2 qubit gates you can do not exactly, you have to make an approximation, but you get to control how much approximation it is. And you can actually trade accuracy and cost as much as you want. So you can either work to sort of perfect accuracy at a exponentially growing cost maybe, or you can work at a fixed cost and just kind of see what accuracy you get, which is nice. So let's say the simplest case would be, let's say you want to act a single qubit gate on a wave function that's stored in this format, this matrix product state format. So you have all these tensors sitting on your computer, these guys in blue here. And here's your gate that you want to act, say, here on the 4th qubit, which is this, meaning really just multiplying this matrix down on this line here. So the way you can do this efficiently and accurately is you can just pull out this tensor out of your state. The other ones don't participate in a step. They're just kind of bystanders. So you pull this one out, and then you just multiply that matrix on that leg. And this is just a very simple thing you can code, like if you're doing in Python with NumPy. We use the iTensor software, which we develop at Flatiron. But let's say if you're just using something you're writing yourself, you would just you call a function called imsum, and you just say sum over this index. And then you can see by inspection that there's 3 indices left over. So you get back exactly a tensor of the same form as what you had going in. And then you just put it back. So you just replace it back into the MPS. And everything's the same in terms of the bond dimension, the rank, the structure. The numbers are different now in this tensor, but that's it. So it's like an exact perfect operation. So that goes really, really well. And then the other one that's more technical, but not that much more technical, is acting with a 2-qubit gate. And then you can do 3-qubit gates and other ones by kind of straightforward generalizations of these ideas. But 2 qubits all we're going to need here. And then the idea is that you just say, okay, this 2-qubit gate's going to act on these 2 MPS tensors because they're the ones that carry these 2 qubit indices or site indices. So we'll pull both of them out. And then we have to contract this diagram involving 3 tensors, right? The 2 MPS cores and then the gate. So this is another diagram that you can just sum either pairwise or altogether by a call to something like imsum or using iTensor. And then you get a tensor with 4 indices, as you can see, going around the outside. And the problem now here that you have to fix is that this has destroyed locally the MPS form. You don't have any more tensors, each one carrying 1 of the qubit indices. Now you have this kind of merged guy, this blob that has 2 qubits, and we want to split it back apart. But then the SVD is the same tool we mentioned before, can do that for us. So you just take these 2 indices here and treat them as a row, and these 2 and treat them as column. Call the SVD, unpack those definitions back from row and column back into tensor indices, just do that part backwards. And then importantly here, you get to choose, this is what I mean about it being an adaptive algorithm and it adapts to which problem you're solving, is that you get to look at the singular value spectrum and you get to decide, again, do you want to work at fixed accuracy or fixed cost or some kind of trade-off of both? And what's interesting, like actually the most interesting one to think about, I think, is fixed cost, because if you work at fixed cost, what you do is you just take the top chi singular values no matter what. And chi is like your budget of how hard you're willing to work on the classical computer. And because you can always work at a fixed cost, you can simulate a circuit of any depth you want. And that's pretty amazing. It's just that you might not do a very good job. But how well you do depends on the circuit. So it's very problem dependent. It's a very interesting thing to try to do. But bottom line is you can do this SVD, you can push the singular values over to the left or to the right. You get back 2 new MPS tensors and you can replace them back. And you get, you can work, say, to the same bond dimension at the cost of a small loss of fidelity. Or you can let the bond dimension grow and then have less loss of fidelity or maybe no loss of fidelity, depending on what you like. So that's kind of the main payoff today. And then we'll kind of wrap up here in a second. So that algorithm I just talked about, these 2 steps, it's called the TEBD algorithm. And that was already described in 2001 by a researcher, Geoffrey Vidal, who was kind of crossed over from quantum information into this kind of condensed matter and tensor networks area. So already in 2001, he had devised this really powerful algorithm to simulate quantum circuits. But I'd say that activity of using it that way didn't really pick up steam more into like 2015 or 16, and maybe even a little bit later than that. But now it's something people are using quite a lot, and they're using it to run different quantum circuits and actually see, sometimes for the first time, how much entanglement actually is there in these quantum circuits. You know, it wasn't always known when those algorithms were first written down. But so basically, here's a kind of cartoon of all these pieces put together. So we can push this MPS through. We work at some kind of fixed rank, for example. The fidelity might go down a little bit, but you know, maybe not that much. Like maybe it just goes down to 0.9, and we get the whole state afterward to some good approximation, and we could see a lot about the quantum state and see a lot about what how the simulation goes and understand the real sort of cost of doing these algorithms on a classical computer. So, as I mentioned, you could also work at sort of perfect accuracy or sort of fixed accuracy. And in the worst case, the bond dimension, the rank, will double every layer. So you could actually work at perfect accuracy for a certain number of layers. So this is the last, like, say, 3 slides, just thinking about what are the different kind of limits of this, trying this out on abstractly on different circuits. In the worst case, in terms of classical cost, the bond dimension would just double every layer if you wanted to do like a perfect job. That's an exponential growth, but only powers of 2. And because it's only powers of 2, and we can handle easily bond dimensions of 1,000, even more than that, then at least 10 layers is of any circuit, any circuit whatsoever, random circuit, any algorithm you know about, is always possible, no matter how many qubits, even thousands of qubits. So I'm just showing below what is today, and on a laptop, an easy simulation would be, imagine the circuit going down the page for thousands more qubits and 10 layers. This is showing actually 10 layers. We could do this in a matter of minutes on a laptop, no problem. So that's an easy limit actually for classical computing. Another easy limit is infinite depth, any number of layers you want, basically, as long as the number of qubits is fixed. This one is more well known. So this is the idea of just, you could work in the full Hilbert space. And we could do this with an MPS or just a full tensor. So that's another limit that's easy for a classical computer. Just store the whole state. It's not that many qubits. And when you put this picture together, there's a nice picture you can develop that really helps us to see the shape of the kind of classical computing boundary. And the shape is basically that, as I mentioned, we can do shallow circuit depth. So Y is circuit depth, X is number of qubits. We could do shallow enough circuit depth. You can go to any number of qubits you want. Really thousands of qubits, no problem. Or you could sort of work at a fixed small number of small to sort of medium, say up to 40 qubits, and go to any circuit depth you want, and kind of a linear cost as well, linear and circuit depth. And then some boundary in between that kind of trades off between these two. And this direction, if you kind of go this way, is a direction where you're limited by, tensor networks are limited by how much entanglement there is. And so you might even find that you can actually push this boundary pretty far out. Like, see, I'm not putting numbers. So we don't, for any given algorithm, we don't know where this boundary is until we try. And it might be that the algorithm actually never needs that much entanglement. And maybe you just end up sitting here and we can just do it. And we can kind of do it on a very large number of qubits. Or other algorithms might be way out here. Like Shor's algorithm is one I believe is much more like out here. And we wouldn't be able to really simulate it on very many qubits. We could always do a few, but not very many. Okay, so that's kind of it for the slides for today. So kind of a more technical talk just to set things up. To preview for Friday, what are some applications of simulating quantum circuits? So there's two slides, just kind of saying 2 that I'll show on Friday. One of them is that I was involved last year with a really talented student and with my old postdoc advisor, Steve White, trying to simulate Shor's algorithm. And we realized that the first half is really hard, like as many people expected. But we were surprised to find that the second half of Shor's algorithm, which is just performing a Fourier transform using an algorithm called the quantum Fourier transform, turns out to be easy. And in fact, so easy that the whole algorithm itself, independent of the state you put it on, the whole circuit actually can be compressed once and for all as a tensor network. So it's like, and it's a small tensor network, like the bonds are rank 8, chi equals 8, approximately, to a very good approximation. So it's such a small compression of that circuit that I could actually email you a file that just has the entire circuit computed once and for all in a little file that just holds that tensor network. And you wouldn't actually have to run that algorithm. You could just use that compressed form of it for any input you want to try. It turns out to be a pretty surprising thing. It's like we were able to almost pull that algorithm entirely from the quantum world all the way back into the classical world, with one caveat, which is that you have to be able to represent the function you acted on as an MPS. But that turns out to not be such a bad restriction, because it turns out you can represent a very, very wide range of functions as MPS. So here I'm showing one input we tried, which is just a single cosine function. That's very easy as an MPS. But even this pretty awful function that has sharp cusps also compresses as an MPS really well. And then the neat payoff here was that it turns out to be a really good classical algorithm. So using these tensor network tools, we could run this on a fine grid on 1D. And by taking the grid to be finer and finer and finer, here's a crossover around 2 to the 18 grid points going from 0 to 1. It actually starts beating the fast Fourier transform. which is kind of the previous contender of one of the fastest known, most efficient algorithms in classical computing. So there it's shooting up, and our quantum Fourier transform just stays about the same cost. So I'll talk in more detail about how that works. And then the other example that I'll give, and we've had a few different activities here, but these are just two, is that we saw a paper just from a couple months ago by a group at IBM that was studying kind of a condensed matter problem, the Ising model, undergoing what's called flow K dynamics, just these kind of stroboscopic dynamics in time on a certain lattice called the heavy hex lattice that they were interested in studying. It's the lattice of their device. And the experiment, the idea was that they could go to some times that might be very, very hard for a classical computer to reach. But it turns out by using these same kind of tensor network methods I've been going into some detail about, one of the postdocs here at Flatiron was able to actually simulate those dynamics to extremely high accuracy. And there's some of his latest data here in this dashed line. And there's the experiment with error bars. And what's really good news, I think, for the field is that the experiment looks to be very, very accurate. It's just that the problem also can be done classically. So there's kind of a nice handshake now that's possible between these experiments and the classical simulations. Okay, and that's kind of all I have for today. So thanks for sticking around. So tensor networks are this very powerful tool to work in high dimensional spaces and do linear algebra in these exponential spaces. And they're really ideal for simulating quantum algorithms. Also, all quantum circuits are tensor networks if you know how to look at them. So it's kind of a hand in glove fit of this tool for this class of kind of algorithms and problems. And this boundary is being defined right now, I would say, better and better between kind of quantum algorithms and classical algorithms. So thank you.
Super. That was really, really great. We had some good questions in the middle. Let's see if we've got one here.
You mentioned a big caveat for the quantum Fourier transform is that the initial state has to be a matrix product state.
Correct.
Can you give an example of something that isn't a matrix product state?
Yeah, it's a great question. So I kind of hit it on this plot, but in the plot in the paper, we show way up here, we show just random function, like random meaning if we had 2 to the 18 grid points. So imagine finely chopping the unit interval 0 to 1 and 2 to the 18 small chops, if I then just put a totally random function on that grid, that's the worst case. And so in MPS, you can fit it into an MPS, but the bond dimension, the chi, just blows up exponentially. And then it's actually way worse than the fast Fourier transform in that limit. So random would be the most extreme example. But then other examples would be, for example, if you summed sort of delta functions, like just put delta functions in the unit interval at like random locations. That would be another one where the bond dimension would basically be equal to how many delta functions you put. And you could make that be as big as you want as well.
Do we have to worry about stuff like that? Or is that just very rare or very point where, one wouldn't need to worry about that?
I think it's a really interesting question to unpack. So we've been thinking about this a lot since we realized this like last year. I think the kind of quickest answer is I think we don't have to worry about that all that much in the sense of kind of, real world problems, meaning like solving differential equations, which is where we're trying to use this. And not only us, but some other groups are trying to use this now as a tool within the kind of toolbox of all kinds of applied math problems, like solving differential equations, where you use the Fourier transform to do a kind of splitting process to integrate in time. It's kind of a well-known use of the FFT. So we're trying the QFT now for that same thing. There, the functions are pretty smooth, because you would say time evolve a fluid flow and it's smooth, and then it gets more turbulent, but it's not random, it has a lot of structure. But that's an interesting case, because then as it gets more turbulent and more chaotic, the MPS bond dimension grows and grows. And so you can kind of really tie it to some kind of information theoretic thing where after a while chaos takes over and you can't really store it anymore. But that's true anyway of other function representations. But then back to quantum computing, this is currently my kind of rough understanding of why kind of solving this QFT part doesn't totally solve Shor's, and it doesn't it doesn't solve factoring, is that the rough understanding I have of what the state is like after the first part of Shores, where you're doing this kind of period finding thing that I could talk about more, is that I think it's essentially putting delta functions in random locations into the state. So it's well known to experts on that algorithm that the chi, the bond dimension, is the size of it is the number you're looking for in Shores. And that number is known to be very large in a typical problem that you're doing.
Thanks. I think that
Yeah.
Super. Daniel, any questions from your side?
No, it was very well explained. I'm quite excited for Friday.
Thanks a lot.
Super. Yeah, I guess maybe just following up on Shor, because I was, before you came to the slide, I wrote to myself, oh, what happens with Shor's algorithm?
Yeah.
So I guess the point of Shor is why it's the speed up comes from this exponential exploration of the full Hilbert space, and that's really where the tensor network is not able to win.
Yeah. So here's kind of it's a great point. It's like, here's kind of my mental, picture for how it would go if you kind of try to imagine what the quantum state is like in Shores. So the brilliant thing about Shores is the circuit is really shallow, like in the sense of, in a scaling sense, like if you actually just count the number of gates, it's like brilliantly few gates relative to how hard the problem is. So it's a really, I think, the most impressive quantum algorithm by far. And then what's sort of also really essentially important about Shores that I think is sort of missing, I think, in some of the newer proposals sometimes that people make for quantum computing, is that it really uses the fact that the state could get really highly entangled, which is the essential, from the tensor network point of view, that's the essential reason to have a quantum computer. I mean, if it's not entangled, we can always simulate it. So right. It's like the sine qua non, of quantum computing from our point of view is like, it better be entangled at some point. So the view I have of Shores is that it's like you're basically running a random number generator, like kind of like a linear congruential random number generator. And you're generating these random numbers, and then you're storing them in the wave function. And the circuit is very shallow, so it puts them in very fast, like in very few operations, it's sort of running this random number generator and storing all the outputs as these kind of delta functions in the state. But because it's like a random number generator, they're just in random places, and the tensor network cannot compress it. It just has to memorize them. And because they're big numbers that you're trying to factorize, that process is a really long period. So the tensor network just has to memorize them all. And so the bond dimension just explodes. But the quantum computer, the magic is that it can just in principle, hold on to all of them and build them up very fast. And then the QFT runs and just, essentially counts the period. So we just can't hold on to that many sort of random points, basically, that have no real pattern to them.
Very good, very good. And then maybe just a last quick question. So if I understand this particular slide correctly, so you have some function that's defined over some number of grid points, and if the number of grid points becomes huge, then the classical implementation of the quantum algorithm for the Fourier transform wins over the fast Fourier transform. And I guess the question is, in terms of practical applications, when there, I don't know, industry or whoever's doing Fourier transforms, is it common for there to be that many grid points where it would be faster to do it on a tensor network?
Yeah, that's a really good question. So that's something that, I realized that I was like out of my depth when we first noticed this. And I mean, in fact, some other people had noticed this possibility before us. There's a paper by some Russian authors a few years ago where they had pointed this out, but they didn't quite have the last part, which was the entire circuit compressed, which that's the thing that we got. But then I've been talking, fortunately at Flatiron, we have some really leading applied math experts, because we have a whole applied math center downstairs in our building. So I've actually been talking to them now about these questions and saying, okay, what are the real world cases where you actually need 2 to the 20 grid points? Because as you are guessing correctly, that's not always the case, right? I mean, you can often get away with 2 to the 10 could be fine for a lot of problems. And where that's still something that we're mapping out, but they're kind of assured me that there are problems. And I think some examples would just be when the function is just getting really detailed structure, like an example could be like a turbulent fluid flow, and it's getting lots and lots of very fine structure. So that's really the idea of the Reynolds number. It's like what's the kind of ratio of the smallest length scale to the largest, or the other way around, I forget. And it's saying, it's saying kind of how many levels of structure are there in the problem. And you really might need to zoom in a lot and hold on to these very fine details to accurately do the problem. That's one example. And then the other key payoff could be not so much 1D, but really when we go to 3D. So there, the crossover may happen a lot earlier for fewer grid points in each direction, because it's like all the points in X times Y times Z. So we could get an earlier crossover.
Okay, so looking to patents, and then you going to work for or something.
Yeah,
okay.
We want to see what this thing can do.
Yeah, very, very cool. All right, so I think that's everything. And you've given us a huge amount of time, and I agree completely with Daniel. This is an incredible pedagogical introduction. So thank you very much. Really, really appreciate it. So let's thank Miles.
Thanks, Will. Thanks, everybody.
Yeah, and then looking forward to seeing you Friday.
Looking forward.
Thank you.
Thank you.